What if engineers could create a virtual copy of an entire power system and use it to test problems before changing the real grid? That's the idea behind a digital twin. A digital twin is a virtual representation of a real physical system that is connected to an information from the real world. The physical system exists in the real world, while the digital twin represents that system inside software, where engineers can observe and analyze it. Modern power systems are becoming more complex. Renewable energy, batteries, electric vehicles, smart devices, and changing electricity demand can make the grid harder to predict. The connection begins with data. Sensors can measure things such as temperature, vibration, voltage, current, equipment condition, and other operating information. Engineers combine this information with engineering models and software to create a virtual representation of the real system. The important part is that the digital twin can change as the real system changes, allowing engineers to see a more current picture of what is happening. Because the model exists virtually, engineers can test different conditions without directly experimenting on the real power system. Engineers can also use simulations to explore possible future conditions, such as overloads, equipment problems, changing demand, or renewable energy fluctuations. The basic idea is simple. Collect real data, update a virtual model, simulate possible situations, and use the results to make better decisions about the real power system. A digital twin needs reliable information. Sensors and monitoring systems continuously provide measurements that describe how equipment and the grid are operating. Software models can represent individual pieces of equipment, such as transformers, generators, batteries, motors, and other important grid components. These individual models can also be connected to represent larger sections of the power system, or even an entire grid. By tracking equipment behavior over time, a digital twin can help engineers identify unusual conditions that may indicate developing problems. Instead of waiting for equipment to fail, engineers can use digital models and historical information to support predictive maintenance and plan inspections earlier. Engineers can also simulate faults. For example, they can remove a transmission line in the virtual model and observe how the rest of the grid responds. Digital twins can also help engineers study renewable energy, where solar and wind generation can change with weather conditions. Engineers can also test future demand scenarios, such as growing cities, new factories, electric vehicles, and increased electrification. The goal is not simply to create a beautiful virtual model. The real value comes from helping operators and engineers make better decisions. A powerful digital twin creates a continuous connection between the real system and the virtual world. Measure, model, simulate, decide, and update. One major benefit of digital twins is early problem detection. Engineers can explore possible issues before they become serious problems in the physical grid.
Digital twins could also help integrate more renewable energy, allowing engineers to test how solar, wind, storage, and demand interact
before making major changes. Before building new infrastructure, engineers can use digital models to explore different designs and see how new equipment could affect the wider power system. Digital twins could also become powerful training tools, allowing engineers and operators to practice responding to difficult situations without putting the real grid at risk. But digital twins are only as useful as the information behind them. Missing, inaccurate, or delayed sensor data can reduce the quality of the virtual model. Another challenge is complexity. Large power systems contain thousands of interacting components, making accurate and useful digital models difficult to build and maintain. Because digital twins can connect to important infrastructure, cybersecurity and trustworthy data become essential. Engineers must protect both the physical system and its digital representation. In the future, digital twins could become even more closely connect artificial intelligence, automation, and smart grid technology, helping power systems respond faster to changing conditions. The big idea is simple. Digital twins give engineers a virtual laboratory for the power system, one where they can observe, predict, and optimize before making decisions in the real world. And as grids become smarter and more complex, the digital twin could become one of the most powerful tools for building the reliable, flexible, and intelligent energy systems of the future. Thanks for learning with Ethan. If you enjoyed this lesson, don't forget to like, subscribe, and turn on notifications so you never miss another easy-to-understand engineering video.